one is Contractor Daniel Serrano Delgado, and he will talk about principal G bond. What is a G?
Good morning. At this point, correctly.
I think it's a smart webcam, so it looks.
Okay, so good morning. The connections of principal G bundle. So give a reminder of what in particular this right action of a Lie group is. So well, let G be or and we'll say that a smooth right action this Lie group on a manifold is a smooth map from M times D to M such that we basically multiply well, we have the product at the right by G an element of our Lie group, and it has to satisfy a set of conditions. First of all, if for all elements X in our manifold M and G and H our Lie group G, we must have does this look?
Can you see the presentation?
Yes.
Fantastic.
All right. So such that for every element or manifold, the identity element of our Lie group is X, and we must also have associativity elements. In such we say that G acts as smoothly on the right on your manifold. Now we'll say this free stabilizer of every point the group that only contains entity element. Equivalent to say that equals X only if now a manifold M will a G manifold. And now so if we have a manifold M, we're gonna say that the map F from M to M is G equivalent the following conditions satisfied for all X in M times D. And now with the most important preliminaries already stated, we're ready to see what model is. So we have a smooth it's a smooth principal G bond. Smoothly and freely for total space, right? And the following fiber preserving local realizations are G equivariant. And we're on the right in this way, as we see at the end of the slide. Now, do so formally. But this proposition tells that, okay, so we have our principal G, D2 amps always, On P, the formatry, this bundle's canonical, will be notified. And it's just of or tangent space. And also, which we'll call a. So this completes, but this is not necessarily well defined. The vertical is. So, well, as it's stated here, we'll have that equals of and frontal distribution. We'll start with this definition. We say that a connection for P here G by omega, and well, this connection in P satisfies the following conditions. Any element of our algebra have this equality, and as a second, finally, that our one form is smooth. Does have to do with the demand we were talking about distributions. As a matter of fact, they are indeed related. So if we have on P, we can be a G-valued one form. On P, P from the tangent space in P to the vertical tangent space P, and is such that it has a kernel HP. G, one form that is the identity on the vertical space at each point P. To be the kernel of P at each point. This is like an overview. And sublime. But what this tells us is that connection is essentially the choice of horizontal complement to the vertical space. It is this choice of total distributions. Connection is this choice we make for her. So for this presentation, I use two books on differential geometry and the Robin Flamenco and Navi geometry. I did read actually on Navikov's book. That basically said further on. A bit Can I hear us?
¿Y ahora?
Can you hear us now? Can you hear us?
Sí que el sonido viene intermitente, pero no sé si será por parte de nosotros o por la conexión de él, podría ser.
So when you're speaking, I hear you well, but when the speaker is speaking, it's like it kind of stops for a few seconds and then comes back.
Sorry to hear that. So you couldn't hear Daniel's presentation?
No, I hear it, but towards the end it got like kind of intermittent. But when you were speaking in the audience, for some reason it's clear. But maybe maybe if you make it closer to him, it will be better. I don't know. So.
They seem to have like shared microphones or.
Sí, pero no tenemos.
Okay.
Estamos en proceso de.
I'm really sorry to hear that, Daniel.
No, it's I got the most of it. So.
So you get the idea of Daniel's presentation.
Yes.
Okay. So, have any questions to Daniel?
No question. I think it was very clear, and there's a lot to learn in this field, and you're in a very good position to do it with all this preparation from this program. So yeah, looks like you really mastered some important concepts.
Good. Thank you, Daniel. So, you don't have any question with them? No. Then we
Thank you.
continue. Thank you, Daniel. So we continue with Gracio's presentation.
¿Será terminado?
Yeah.
This is what say. Yes, the last version, the one from 840. Okay, sí, bueno, sí, debe ser eso.
Okay.
That's the second version.
Gracio will talk about the Steiner's symmetrization, so all yours, Gracio.
Okay, thank you. So, good morning. Okay. I'm going to talk about the generalization. Oh yeah. Okay, here is a drawing of how it works, but I will explain it later, so we can continue. So, first of all, we need to remind some things, like, for example, if we have some number which is greater or equal than 2, a convex body in Rn is a subset A such that A is convex. Also, A is compact, and A has no empty interior. And well, also we have the Euler volume of A, which is defined as the product of the volume of A times the volume of the polar body, where the polar body is given by this expression right here. Okay, so Steiner symmetrization was introduced by Jacob Steiner around 1836. Well, this was, well, he introduced this in an attempt to prove the isoparametric inequality. So the isoparametric inequality states that when you fix a parameter, the circle maximizes area among all closed curves. So here is a drawing, well, for the plane, the isoparametric inequality says that, well, 4p times the area is less than or equal to the perimeter square. Well, the equality is only, well, we get equality if and only if
the curve is a circle. So it turns out that Steiner's proof was incomplete, but the modern standard way still uses Steiner generalization. And well, this technique, well, this process, I guess, is used in analysis in PDs and many other branches of mathematics. So, what is Steiner generalization? Okay, well, first of all, we need to talk about what is asymmetrization. So we are going to take some positive integer n, and we're going to take some I from 0 to n minus 1, and we're going to take also a subspace H that is high-dimensional subspace of Rn. Well, we're also we're going to take some class of non-empty compact subsets of Rn B, and we're going to let B sub H be the subclass of members of B which are symmetric with respect to H. And well, this is called as H symmetric. So here is some visual example. So this first one is H symmetric because when you reflect any point with respect to H, the point is still on the set, but the second is one set which is not H symmetric. So finally, what is a symmetrization? Well, it is any function which goes from the class B into the class of symmetric sets B sub H. Well, this can be called as isymmetrization or simply asymmetrization. And the image of this function on some set is called as the symmetral for that set. So basically, asymmetrization is a way of transforming some set into one which is H symmetric. Okay, there are many properties that asymmetrization might or might have or might not have, such as monotonicity, which means that it preserves set inclusions. It might be F preserving, and that means that for some function F of interest, which goes from the class B to 0 to infinity, like for example volume. Well, basically it preserves that. Well, that F maps the symmetral to the same thing as this set K. And well, we might also have idempotence, which means that if you apply this function 2 times, you're going to get the same as applying it 1 time. And well, there are other properties such as invariance on H symmetric sets. We also have invariance on H symmetric spherical cylinders, for example. We might also have invariance on orthogonal projections with respect to H. And we might also have invariance on the translations orthogonal to H of H symmetric sets. So finally, what is Steiner symmetrization? Well, it is the n-1 symmetrization. So here H is a hyperplane. So it is the symmetrization S sub H going from B to the class B sub H that maps every K into the symmetral obtained by the following construction. So first of all, we take every single line G orthogonal to H and intersecting K, and we consider the line segment of length the one-dimensional volume of the intersection of that line with K. Also, we move each line segment L that we constructed along the line G until its midpoint is in H. And well, the union of these disjoint line segments is going to be our symmetral. So here is some visual example to do that. So we choose some subspace H, right? Like for example this line, and we have some set K. Now we take all the lines which are orthogonal to H and that intersect K. Now we are going to measure the one-dimensional volume of those intersections which are in red. Now we're going to construct some line segment of that length, and finally we have this new set, which is going to be our symmetrical. Okay, and maybe could you go back? Yeah, thank you. Okay, and as you can see, this is symmetric with respect to H, right? Okay, now in general, we can have something called the Schwarz symmetrization. In this case, we take some I being in 0 to n minus 1, and the Schwarz symmetrization is going to be the I symmetrization. So here H is I dimensional. So it is the function S sub H going from B to this class B sub H that maps every set K into the symmetrical obtained by the following construction. So for each translation G of a n minus I dimensional subspace orthogonal to H that intersects K, we consider a n minus I dimensional ball beta with volume the n minus I dimensional volume of G intersected with K. Now we move each ball through G until its center is in H, and then the union of this disjoint balls is our symmetrical. So here is a visual example. So again, you can take some subspace. So in this case, this is a line which is one dimensional, and we have some set K. Now we take the orthogonal. This in this case 3 minus 1 dimensional subspaces which are orthogonal to H, and that intersect K. So in this case, those are these planes. Now those intersections have some volume. Well, some 2-dimensional volume, and we measure that. Now we construct balls which have that volume, and we put them in such a ways that their center is on H. And finally, well, the union of these balls is going to be our new symmetrical. So it turns out that Steiner symmetrization satisfies all properties that were mentioned earlier. Well, all of this.
Okay.
Yeah. And well, Schwarz symmetrization also has all these properties except for invariance on H symmetric sets. So default property. Okay, there is a nice characterization of the Steiner symmetrization. Well, it turns out that the Steiner symmetrization is the unique n-1 symmetrization on the class B of convex bodies of Rn, such that it is monotonic, it is volume preserving, and it is either invariant on H symmetric spherical cylinders or projection invariant. So what about convexity and Mahler volume? Well, actually, Steiner symmetrization has the following properties. It preserves convexity. It also increases the Mahler volume. It preserves central symmetry with respect to the origin, and it reduces perimeter. But why is this useful? Okay, so a ball is like the most symmetric object, right? Because it is symmetric with respect to every single subspace. On the other hand, Steiner symmetrization helps us to make some set symmetric with respect to a fixed subspace. So if one takes like several subspaces and one apply this like many times, like can we transform some set into a ball? And well, how many subspaces should we use? Well, at first it is like intuitive that one should make the set symmetric with respect to every single subspace. So one could think that one needs every single subspace. Well, actually, no, yeah. Actually, no. One can do this with just a sequence of subspaces, and but yeah, but an infinite number of subspaces is going to be necessary in general. And well, for that reason, because we want like to apply this infinite times to some set, we need like some notion of convergence. So it is possible to consider some metric called the Hausdorff metric over all convex bodies, which is given by this expression. But basically, it is the maximum distance which a point of one of the bodies A or B can have from the other body, basically. Well, this metric gives well, induces a topology, and this gives us a notion of convergence. And well, this is the Hausdorff topology on convex bodies. So the magic of Steiner symmetrization is that one can transform every set into a ball with same volume. Well, every single convex body. Okay, so for all convex bodies A, there exists some sequence C0, C1, C2, and so on of convex bodies, each obtained from A in a finite number of Steiner symmetrizations, such that this sequence is convergent to a ball B with center at the origin, and this ball has the same volume as the set A. Well, in particular, this can help us to compute the volume of a convex body, and one can also think of numerical methods to approximate it with this. Okay, so basically, one can do that taking some sequence of subspaces and taking the Steiner method with respect to H0, then this result well, then take the symmetry with respect to H1 of that result, and so on. Well, this is going to converge to a ball. Yeah, this is going to converge to a ball centered at the origin with same volume, but there is for some sequence, so it is not any sequence. Okay. Well, actually, this result can be improved because one can consider just a finite number of subspaces, but applying each one of them infinite times. Okay, it is like some periodic sequence. Well, it turns out that one can do this. Yeah. So well, here, well, I wanted like to put here like some video, but I had problems. So let's pass each one. Yeah. So this is like yeah. This is like the process of making some set into a ball with Steiner symmetrization. So as you can see, this gets rounder and rounder until yeah. Well, in the limit we get a ball. So there are some consequences of this, such as the generalized isoparametric inequality. So it says that for any convex body A, we have this inequality where P is the perimeter of A or P, and well, this event is the n-dimensional volume, and here P is the ball center at the origin with radius 1. So I will do the sketch of the proof of this. So well, one can prove that there must exist some n-1 dimensional subspaces H0, H1, H2, and so on, such that this sequence of iterated symmetries converges to a ball with this modification to its well, it's called like scaling, right? Okay, yeah. Well, one can prove this, that there exists such subspaces such that we have this. Also, we have continuity of the perimeter and the fact that the perimeter is increased by Steiner symmetrizations. So the perimeter of A is going to be less than or equal to the perimeter of the symmetry of with respect to the first subspace. And well, that is going to continue descending forever. But this converges by continuity of the perimeter. This converges to the perimeter of this because this sequence converges to this. So this is going to converge to this perimeter, and well, now you just compute this perimeter, and this is equal to this. Well, if you take this one, the perimeter of B, and you divide to the other side, and also you how do you say elevar al line?
Take the amp power. Yes.
Yeah. Yeah.
Power is.
Okay. And then you are left with the inequality we saw on the corollary. Well, that's one consequence, but there's another one, which is the Blaschke-Santaló inequality, which is the following. So it says that for any convex set, convex body A with central symmetry with respect to the origin, one has that the mother volume is less than or equal to the volume of the ball squared. Well, here B is the ball centered at the origin with radius 1. Well, there are many other theorems, but we're going to do the sketch of that one. So again, there must exist some n-1 dimensional subspaces, H0, H1, and so on, such that this iterated sequence of symmetries converge to that scaled well. And well, we also can consider the polar of this member of each member of this sequence, and it turns out that one can show that this sequence converges to this other ball. So the difference here is that B is down here, and B is up here, and A is up here, and A is down here, basically. So because of central symmetry and continuity of the volume, one gets the following: that the mother volume, which is the volume of A times the volume of the polar body, this is less than or equal to the volume of the symmetry of A times the volume of the polar of the symmetry of A. And well, that keeps like growing until it converges by continuity of the volume to the product of the volume of this ball and the product of the volume of this ball. Well, when you compute this is equal to the volume of the ball squared. Well, here are some references. I was going to talk about the procedure that Professor Rubinstein told us about triangles, you know.
Yep.
But I thought that maybe I was like, well, that this was like long enough, maybe. So I decided to left that outside, but yeah. Well, here are some references. This is well, these are some notes that GANA REU is working on. This is some book on convex and discrete geometry, and these two are our papers from this journal. Thank you.
Thank you, Gretchen. Are there questions or comments? Daniel, can you hear?
Yeah, can you hear me?
Yeah, fantastic.
Very good. Yeah, I heard everything. This time was very clear. So the microphone somehow moved, so it was good. When you do the Schwarz symmetrization, what happens if I equal to 0?
Okay, can you please go back? Es bastante atrás, entonces es por los dibujos que eran como 3D. Yeah, those. No. Yeah. Okay, when H is zero-dimensional. Well, it is just the zero vector. So
No, not H zero-dimensional. I is equal to 0.
yeah, but this space H has I dimensions.
Yes,
So,
yes. Right. So then you're right. Exactly.
well, I think that doesn't make sense actually, because that's the zero vector and like you need to yeah, and so I don't think that this makes sense. So I think that's a mistake, and it's well, this is actually from 1 to n-1, I guess.
But in the definition, you have I could be 0, right? And then you take
Yeah, one of those papers says, well, like says that like you can take I equal to 0, but I'm not too sure about it, and maybe it is, and well, a strange case. So maybe I guess I would omit it, but I didn't notice this yesterday.
okay. Yeah, that was just a small question. Otherwise, I think maybe you can say a little bit more why the Malloy volume will increase
Yeah,
with the symmetrization.
yeah, but at the end, well, because it was getting like too long, I decided to omit that. Yeah.
But maybe just your intuition, like why the Malloy volume will increase.
Well, I think well in the Schwarz implementation, for example, one is taking like circles, well, balls, and balls are the maximizers of Malloy volume. So I guess that maybe if you maximize every single slice, maybe you are going to get something which bigger Malloy volume, but that's not a really good justification. But I guess because of that, because every single slice is like the maximizer of the of one of some dimension below, but I don't really know.
So maybe just when you look at definition of polar body, right, you need to look at all the inner products with the original body less than equal to 1, right? So if your body is like not very regular, it's kind of spread out,
Yeah.
then that puts more restrictions on the polar body. But if it's more centralized and symmetric, then somehow polar body can be more spread out. So you're fixing the volume of the body, but the volume of the polar body will increase in this process. That's the intuition, I guess.
Okay.
Yeah. So Malloy volume will increase because it just means the polar volume is increasing.
Yeah. And well, actually, in the last corollary, I saw that proof in which they like make it like es que como se dice como a pata, no sé, como manually and well maybe well where they show this like manually, but actually I didn't saw a proof that Muller's volume is increased, but can you please go to the last corollary? To the proof. Well, the sketch. Okay, okay, that one and the proof. Yeah, okay. No, it's the other one. No, below. Yeah, below. Yeah, here. Yeah, thank you. Okay, like here, like they show this like manually actually because they're taking this volume map and they are using some sequence which converges to some balls and they show like these increases there and well there is where it is necessary this central symmetry of the convex body because this volume, the volume of the symmetrical, well, the volume of the polar of the symmetrical is greater than the volume of the polar of the body. Well, that's well for that inequality, one uses that that the body has central symmetry. So maybe here is like the manual way of proving this, but I guess the argument must be something like this, maybe. Well, yeah, this should prove that Muller's volume increases, actually.
Are there more questions or comments? Are you still there, Janir?
Yes.
Okay. So let's thank Greshu and also Daniel once again. Nothing.
Thank you very much.
Experience. I don't know if you have any final comment, Janir.
No, I'm very impressed. So it's like a presentation of a PhD student, so both of them really did a great job, and I think very proud of everybody. So yeah.
I'm glad you like it.
Yeah.
Good. So I will talk to Felipe to post all the workshop information in the web.
Great. Yeah.
And I will let you know.
Very good. Yeah.
Good.
Yo sí quisiera arreglar lo del cero, porque creo que lo del cero sí está muy raro, entonces si usted me deja arreglar eso y yo se lo paso y...
Excellent.
Okay.
Okay. So it's been a pleasure. I hope we can work again next summer. Well, next Costa Rica's summer. And maybe we can improve some of our activities and get a little bit more how do you say, more public, more students. It will be fantastic. Thank you very much, Janir, for the inventive, and we deeply appreciate it. So
Yes.
thank you very much,
Ronald, for organizing. Thank you very much, and for the students, just keep learning, keep exploring the boundaries, and anytime you want to reach out to me, of course, I'm always available. So yeah.
Good. Thank you, Janir.
Okay.
So bye.
Take care. Enjoy your summer.
Thank you.
Take care.
Thank you.
Bye.
Take care.
to